A few weeks ago, a member of the computer vision Reddit asked this question. Assuming the white is a perfect square and the rings are circles with standard dimensions, what's the most straightforward way to map this archery target to a top-down view? There aren't really many distinct key-pointable features besides the corners. Creases don't count, not all the images have those, but usually only one or two are visible in the images, so I can't do standard homography. Should I focus on the edges or something else? I'm trying to figure out a lightweight solution to this. Sorry in advance if this is a rookie question. I posted a response on Reddit outlining the approach that I would take to such a problem, and I thought it might be worth making a video demonstrating step by step how to do it in OptimEyes Developer. Before I get into my solution, there are a few issues that I want to point out that are important to consider with a problem like this. First, as the original poster said, there aren't many features in the image at known coordinates that can be readily used to create a transformation matrix to flatten the image. As you may know, to create a transformation matrix, you need to be able to locate 4 points in the image, no 3 of which are in a straight line with each other, and you need to know what coordinates those points should appear at in the flattened image. In this image, there's really only one identifiable point, which is the one visible corner of the target, and even that point isn't all that well defined. You could probably get a more accurate location using the intersection of the two visible sides of the target, but even then you'd only have one identifiable point. A third edge on the left is partially visible, but the target is so wrinkled along that edge that the intersection of that line and the top line would probably be quite a ways off from the actual location of the corner of the target. So the first question is, how are we going to come up with 4 points that we know the coordinates of in order to make a transformation matrix? And yes, there is a solution. The second issue, which as you'll see in a minute affects the solution to the first, has to do with the shape that the target circles form in the photograph because of the camera being off to the side and the target leaning backwards. You may know that a circle viewed at an angle will appear as an ellipse. However, what you may not have realized is that the center of the circle does not appear at the center of the ellipse. Let me show you an illustration I created to help explain why that is. In this image, you can see that we have a circle with green lines passing through its center. When a photograph is taken of the circle from a camera off to the left where the two red lines meet, you can see that the widest point of the ellipse that the camera sees is closer to the camera than the center line of the circle. So the center of the ellipse is going to be at the point where the vertical red line crosses the green line. Because of perspective, the part of the circle that's closer to the camera is going to appear larger than the part that's farther away from the camera. So the portion of the circle to the left of the red line is essentially going to be stretched out to form the near half of the ellipse, and the portion of the circle to the right of the red line is going to be compressed to form the far half of the ellipse. Of course, depending on how far away from the circle the camera is, the impact on the final image may be significant or negligible, but we do want to take this into account to ensure that it doesn't result in an inaccurate transformation. So let me outline for you the solution that I came up with, and then I'll run you through a script that I created that takes the image that the original Reddit poster shared and transforms it to a top-down view of the target. This next diagram shows you the points that we are going to use to perform the transformation. The line AB is the minor axis of the ellipse formed by the outside edge of the black rings on the target. The minor axis is the shortest line across the ellipse that passes through its center. The reason we're not going to use the major axis, the line that runs from the top of the ellipse to the bottom, is that, as we saw in the previous diagram, that line, while it does pass through the center of the ellipse, it does not pass through the center of the target. It's closer to the camera than the center of the target. And since we don't have any way of knowing how much closer to the camera it is unless we know the exact distance between the camera and the target, the size of the target, and some other factors such as properties of the camera's lens, we have no way of knowing what coordinates on the circle the major axis of the ellipse should be transformed to. On the other hand, we don't have that problem with the minor axis because, at least in a perfect world where the target is made of perfect circles and it's placed on a flat surface, the minor axis will run through the center of the target from the point closest to the camera to the point furthest from the camera. You may have noticed that in the image there are wrinkles in the target, so there is going to be some imperfection in the end result, but you'll see that it will be very close. Back to our diagram, the line CD runs between points where the edge of the black target circle intersects a line perpendicular to the minor axis that's tangent to the near edge of the red target circle. So what we need to do is find the point where the minor axis, the AB line, intersects the smaller ellipse, which is the red circle on the target. Then we'll find a line that runs through that point at a right angle from the minor axis. Finally, we'll find the points where that line intersects the outer circle. Those will be the points C and D. Looking at that, you might wonder how points C and D are any better than the endpoints of the major axis of the ellipse. The reason that they're better is because we can calculate exactly where those points appear on the circle. As I'll show you in just a minute, the point where the minor axis touches the red circle is exactly halfway between the center of the circle and its edge. So if we imagine a right triangle with points at the center of the circle, at point C, and at the point directly below C where the minor axis touches the red circle, the length of the hypotenuse is the radius of the big circle. And as I mentioned, the length of the bottom of the triangle is half of the radius. So we can use the Pythagorean theorem to calculate the length of the other side, and thus we can calculate the coordinates of points C and D. So without being able to locate even a single specific point in the image, we are able to find 4 points that can be used to transform the target into a circle. The final challenge will be to rotate our output image so that it's level, and I'll show you a way to do that as we run through the script. So you've successfully endured all the introductory blabbering. Let's look at the script in OptimEyes Developer that actually makes this work. To run the entire script, we could click the Run button, but first I'm going to go through it one step at a time, showing you exactly what each step does. First, we'll open the image of the target. If we had been connected to a live camera feed, we would have added a step to connect to the camera and then captured a video frame. Next, we change our color mode so that we're looking only at the red color plane, and this is just to help us more accurately find the edges of the red and black circles on the target. Then we do a blob finding operation to find the outlines of the red and black circles. As you can see, I have the blob analysis tool creating an image mask using manual thresholding, with every red pixel value from 0 to 141 becoming black in the mask, and every value higher than 141 becoming white. The blob analysis tool will then use that mask to find the outlines of the blobs in the image. As I adjust the threshold value, you'll see that somewhere right around 141 is where we get the cleanest lines right at the edges of the red and black circles. And then there are a few other options we'll set in the tool. First, we'll have it ignore any blobs whose area is less than 12,000 pixels, and that's a value that I chose by looking at the actual area of the red circle and then going a little lower. And we'll also ignore any blobs larger than 60,000 pixels, which is a value a little higher than the area of the black circle. By setting these limits, we are able to ensure that the tool finds only 2 blobs, which are the 2 that we want to use, and that saves us the trouble of having to figure out which blobs correspond to the circles we're interested in. Finally, I want the tool to store a few numbers related to the larger circle in variables for us to use later in the script. I'll have it store the minor axis angle and the x and y coordinates of the 2 points where the minor axis intersects the edge of the blob. As you'll recall, that will give us the A and B coordinates for our transformation matrix. So with all that set up, we'll execute the blob finding step, and hopefully you can now see that we have green outlines around the black and red target circles. So next, we'll switch our color mode back to looking at all 3 color planes instead of just the red, and then we want to make a line running across the minor axis of the larger blob. That's done using our ROI Manager tool. We're going to create a line ROI, and we're going to name it minor axis. And the coordinates for the endpoints of the line are going to come from the variables that we had the blob analysis tool store. Minor axis int or intercept, 1y, 1x, 2x, and 2y. Then we execute that step, and you see that we now have a line running across the narrowest part of the ellipse, which starts from the point of the target closest to the camera. Our next step is to place a point at the intersection of this line and the smaller blob around the red circle. Of course, the line and the blob intersect in 2 places, so we'll want to be sure that we're placing our point at the intersection nearest us. We'll do this using our lineIntersect script function, and we'll give it the command li1intersect, which tells it we want just one intersection, not all intersections. We'll set our input image to Archery, and we'll tell the function to use the line ROI named minor axis. The ROI that we want to find the line's intersections with is named blob 0.0. The reason for that name is that it's the first child of the first parent blob. The first blob is named blob 0, so the first child is named blob 0.0. Next, we'll specify that we want to find the first intersection between the line and the blob. I'll point out here that the intersections are always numbered from left to right, so from the smallest x value to the largest, and then from bottom to top, or the smallest y value to the largest. And I should also mention that in OptimEyes Developer, y values are specified with 0 at the bottom of the image and going up from there, which corresponds to how y coordinates appear when you're drawing a graph of an equation, for example. Finally, we'll specify a name for the point ROI that we're going to create, which will be a minor axis intercept. So let's step through each of these operations, and then you'll see that we now have a point ROI located at the intersection of the line and the smaller blob. So our next step is to project a line from that point perpendicular to the minor axis. We'll do that using our project from point script function, and here are the settings for that. First, the operation will be make line 2. What that means is that we want to project a line out in both directions from the point. If we had specified make line 1, one end of the line would have been at the point, and the other would have been projected out at the angle that we'll specify. But we want the line to extend in both directions. Next, we specify the image name, Archery, and for options, we specify toEdge. What this means is that we want our line to extend all the way to the edges of the image. We could have specified a distance, but we don't really care how long the line is, so we'll just go all the way to the edge. Now we'll give our line a name, which will be CalLine or calibration line, and I call it that because in OptimEyes Developer, a transformation matrix for an image is called a calibration. Next, the point that we want to project from is minor axis intercept, and then we'll need 2 steps to specify the angle. First, we'll copy the value that the blob analysis tool stored in a variable named minor axis angle, and then, to get the perpendicular angle, we'll add 90 degrees to it. So let's run through these steps. And as you can see, we now have a line ROI running perpendicular to the minor axis through the minor axis intercept. Our next step is to find the coordinates where this line intersects with the big blob around the black target circle. These will be the C and D points that you remember from our diagram earlier. We'll do this using another line intersect operation, but this time instead of li1 intersect, which created a single point ROI, we'll use the command li intersect ves, which will find all intersections and will store their coordinates in VES or visualize script variables. Because of how we'll go about creating our transformation matrix, we don't need point ROIs at these intersections, but we do need to know the coordinates where the intersections occur. The line ROI for this operation will be CalLine, which as you recall is the name we gave this line, and the other ROI is blob0, our parent blob. Finally, the base name for the variables that will hold the coordinates of the intersection points will be calPTS or calibration points. So we'll step through all that, and then let me show you the variables that were created and the coordinates of the intersection points. As you can see, they're named calpoints.1.x, calpoints.1.y, calpoints.2.x, and calpoints.2.y, and you can see what their values are. So now that we have all our coordinates, it's time to create a calibration object. We'll do that using the calibrate script step with the command calibrateImage2. We could have used the command calibrateImage without the 2, but then we would have needed to specify 16 separate variables, one for each of the x and y coordinates of the 4 calibration points in both image coordinates and what we call world coordinates. The calibrateImage2 command simplifies the process by enabling us to specify all the image coordinates in one variable and all the world coordinates in a second variable. So we'll set our input image to Archery, and then these will be the world coordinates of our 4 calibration points. As I explained earlier, we calculate the coordinates of our A, B, C, and D points by knowing that the hypotenuse of our triangle is the radius of the black circle, the bottom is half as long as the hypotenuse, and the Pythagorean theorem gives us the length of the other side. Then we scale the numbers that we get from those calculations so that the final coordinates fit nicely inside an image the same size as our input image with no parts of the target extending outside of the image. Rather than running through those calculations here, I'll just let you imagine how exciting the process was. So next we'll specify a name for our transformation matrix, aka calibration object. And then our last step will be to specify the image coordinates of our A, B, C, and D points. You'll see that I have two if-then steps here, and inside each one there's a step to set the image coordinates. The reason for that is that depending on which side of the target the photograph is taken from, the angle of our intercept line will be positive or negative, which means that the order of the top and bottom points will be reversed. As you recall, the line intersect function numbers the points from left to right and then bottom to top. So to ensure that we have our points in the correct order for our calibration object, we're going to check the y values of calpoints.1 and calpoints.2, and whichever one is higher up on our image is going to be point C in our diagram. Our first comparison will be if point 2 is lower than point 1, and our second comparison will be if point 1 is lower than or level with point 2. So let's see how we combine the coordinates of all of our points into this image coordinates variable. You'll notice that I have the variable substitution checkbox checked, and then we use %n to specify that we want to get the value of a number variable. We want the value out to 2 decimal points, because why not? And then we have the name of the variable, minor axis int or intercept, 1x, meaning the x value of the left side intercept point of the minor axis with the big blob. After that, we have a comma, and that could have been a comma and or a space or even multiple spaces, followed by a similar code to get the y value of that same intercept point. So that's point A from our diagram. Next, we'll move up to point C from our diagram, which is stored in calpoints.1, and we'll get its x value, followed by its y value, and then the coordinates of the other 2 points. So with that, we're ready to create our transformation matrix or calibration object and attach it to our image. And if we look in the calibration tool, we can see that the calibration object has indeed been created. So with all of that done, we're finally ready to transform our ellipses into circles. We do that by having our transform tool perform a perspective transformation, which it does using the calibration object that's attached to the image. And there it is. But we're not done yet because we also need to rotate the image so that the target's level. There may be a way somehow to calculate the coordinates for our transformation matrix so that the image ends up in the correct orientation without having to rotate it afterward, but I didn't want to have to figure that out, so instead what we're going to do is rotate the image so that the top of the target is level. To do that, first we'll find 2 points along the top edge of the target using our Edge Finder tool. If I open this script step for editing, you'll see that it places a line that runs across the edge that we're looking for. When I was creating the script, I drew this line so that it spanned the area where I knew the edge would be. As long as the camera doesn't move too much, this will work. If we need a more robust solution that would work with more camera positions and angles, then we'd have to figure out something else, but this is good enough for now. In the Edge tool, I set a threshold reference value of 61, and that's a number that I discovered with a little trial and error that worked well for differentiating between the white of the target and the darker background behind it. Then I tell the tool to find the first falling edge along that line, where the mask image that the thresholding operation creates goes from white to black. And finally, I set the length of found edge to 0 to tell the tool to create a point ROI at the edge, rather than drawing a line along the edge. And then we do the same to find a second point along the top edge of the target. And let's execute those 2 steps so that you can see the 2 point ROIs. Our next step will be to use the measurement tool to measure the angle between the 2 points we just found. You can see that the start point is set to edge 2 and the stop point is set to edge 1. And in the tool options, we tell it to create a script variable named rotate angle to hold the angle between the points. So if we execute that step, you can see that the angle is 315 degrees. I believe this tool always returns positive angles, so it's 315 degrees rather than negative 45 degrees. So that tells us that our image is currently rotated 315 degrees from where we want it, so we need to rotate it negative 315 degrees to get it back to level. So in this next step, we multiply rotate angle by -1 to change it to minus 315 degrees. And then we use the transform tool to rotate the image. We'll get the angle for our rotation from the rotate angle variable, and we'll set the center of rotation to the center of the world coordinates from our transformation matrix. And if we execute that step, you'll see that the target has been leveled. So now for one last step, we're going to make our final image look a little nicer by masking off everything outside the outermost circle of the target. To do that, first we're going to create an ellipse ROI, which will actually be a circle since its height and width will be identical. We calculate the coordinates for our circle based on the world coordinates from our transformation. Those coordinates were based on the size of the black target ring, which is the 8th line of the target. Since there are two more thin lines outside of the black bars, we need to multiply the size of the black rings by 1.25, or add 25% of the size of the black rings to get the size of the outermost rings. So, knowing the size of the outermost rings and the coordinates of the center of the target, we're able to calculate the coordinates for our circle. So we'll set variables for all of those coordinates, and then use our ROI Manager tool to create an ellipse ROI with those coordinates, and we'll name it Mask Circle. And if we execute those steps, you'll see that we now have a circle running almost precisely around the target. There is a little imperfection caused by wrinkles in the target. Our final step now will be to use our arithmetic tool to make a copy of the image, masking off everything outside of the ROI we just created. If you're wondering why a tool for copying is called the arithmetic tool, it's because it can also be used to add images together, subtract them from each other, multiply them, and so on. So if we execute this step, you can see that we now have our masked image. And just so that you can see the entire process in action at full speed, let's delete all of our images from memory and run the whole script. And you can see that when we do, all of our intermediate images are created, and the final flattened, rotated, and masked image is displayed. I hope you enjoyed this video and that you got something out of it that you can use in your machine vision solutions. To find out more about OptimEyes Developer, visit idealeyes.com. Thanks for watching.